where you're finding the roots. Right? So in problem number 3, from our quadratic notes, the first thing when I go to look at graphing that problem that jumps out at me is I have multiple transformations, and I can't right now describe all of them, but I need them to be able to draw a graph. And the reason I can't describe them all is because inside this parentheses, I actually have 2 transformations going on, and I need to separate them. So the first thing we ought to do is factor out that 4. So 4 times x is 4x, and 4 times 1 gives us 4. That's still all being squared. We aren't changing the problem. We're just writing it so we can list our transformations. That needs to be step number 1. Now we can describe. Let's go one at a time. Austin, tell me what that does to our graph. Well, okay. The very first thing, I try to draw a little arrow here. What do you mean going down? Okay, it does mean the graph's going to be pointing down. What do we call that? How do we describe that? The reflection over the x-axis. It is going to point down, and that's really a very important thing so that when I go over here to draw this, we know kind of what it's going to look like. So we are going to reflect across the x-axis. So that's number 1. I hope you notice how much we are still using those things we did early on this semester. They're not going anywhere. Okay, let's move inside our parentheses. All right, Kelsey, what does the 4 do to our graph? Okay, it's a horizontal compression of a 4th. Now let's talk about shape. Just like Austin described shape for us, what reflection over the x-axis was going to do, what's a horizontal compression of a 4th going to do to our shape? Yeah, it's going to make it skinnier. So we're going to have an upside down, skinnier graph. All right. Let's go to number 3. I'm going to have to underline. I don't have room to write an arrow. All right, Kama, tell me what that does to our graph. So x plus 1. Well, now if it's changing x, it can't go up. All right, changing x. Yeah, not right. Left. Remember, x always tries to trick us. Left is always, we're always doing the opposite. So we're going to go left 1. Just like here, right? We had x times 4, but it's trying to trick us, and it's going to divide everything by 4. Okay? And let's talk about our last one. All right, Isaac, what's that going to do to our graph? We're going to come down 2. So that's skill number 1. Could I describe the transformations? Now, I want to put those into action and actually draw it. Now, that requires, I remember what my parent function looks like. So if need be, draw yourself a little sketch to know what y equals x squared is going to look like so you can remember, okay, as Austin pointed out, when we turn this upside down, when we make it skinnier, what's this going to look like? So I'm going to start, anytime I'm graphing a quadratic, I'm going to start right here at the vertex. Right? If I've got it in vertex form, I'm going to start at the vertex. So I'm going to come left 1. I'm going to come down 2. Reflecting over the x-axis doesn't do anything because we started on the x-axis. And taking 0 and making it a 4th its size doesn't do anything. All right, so we move it left 1 and down 2. We got the vertex. Now, here's what I'm thinking in my head. Don't draw it, but here's what I'm thinking in my head. Okay, I know what this looks like. It's a little parabola. Ooh, that's not pretty. That's gone upside down, and it's skinny. All right. Now, I need some actual points. Now, you can use any points you want. On y equals x squared, you could use the point 1, 1. You could use the point 2, 4. You could use the point 3, 9. It doesn't matter what you use. Okay. You want to try to use something that's going to make it as easy on yourself as possible. There's no really easy for this particular problem. Because part of me says, okay, I'm going to use this point way up here at 4, 16, because 4 squared is 16. And the reason I would think to use this is because of this horizontal compression. Taking 4 and doing a fourth of it is a nice, pretty whole number. The difficulty is I'm way up here on my graph. And so drawing that out is not going to be easy. Because 16 is way up here. Now, we're going to do that point because I want to show you the X part's easy. The hard part there is the Y. So let me kind of estimate here. There's 11, 12, 13, 14. No, I can't count by twos. I could have hadn't already drawn the vertex. I could go back and redraw my vertex and do that, and that would be just fine. So I'm over here at 4, 16. Now I'm going to put a dot there so we can take and move it around. All right, now, we're going to do here a horizontal compression by a fourth. So this X value that was 4, we're going to have a fourth of that. It's going to have an X value of 1. Okay. All right, then I'm going to reflect over the X axis. So instead of being here at 116, I'm down here at 1, -16. Then I'm going to come left 1. So I'm at 0, -16, and then down 2 more. Now, I do know what that point is, but that's not probably going to be all that helpful for drawing my graph. We do have a point, and I'll label it down here. We, in fact, have to know what this is if we wanted to know the y-intercept, because it happens to be the y-intercept. We have a point down here at 0, -18. Now, as Kelsey pointed out, you could count by units of 2s on your y-axis, right? And then that wouldn't be all that bad to end up drawing, okay? Now, if I were going to use that point, I know my axis of symmetry runs right down here in the middle of my graph at x equals -1. So this point I have is 1 unit to the right. So I'm also going to have a little point that's 1 unit to the left. That'd be over here at -2, -16. And I could draw the graph. Okay. So if I'm wanting to only use whole numbers, that would be a very logical point to use the point 416. I don't think it's too bad to use this point right here, the point 2, 4. I will have to do just a little tiny bit of estimating, but it's not bad. So we're going to take the point 24. I'm going to put a dot right here so we can move it around. So there's our point. And I'm going to reflect over the x-axis, so that's the point 2, -4. That wasn't too bad. Now here's where I'm going to do a little bit of estimating. I'm going to horizontally compress that by a fourth. I'm going to divide that x value by 4. Well, what's 2 divided by 4? It's a half. Okay, yeah, so I do have to estimate a half, but I'm pretty good at estimating a half. That's not too hard. And then I'm going to come left 1 and down 2. So here I am at -1/2. Okay, so there's our x value. Right? And then we're down here at a y value of -6. -1/2, -6. So if I was going to count by units of 1s on my y-axis, that's probably the point I would use. It doesn't really matter. That's a half away from our axis of symmetry. So I'd come over here another half. That's -1/2 or -3/2, -6. And then I will sketch out our little curve here. Now, I'm not going to try to get way down there to those points that are way off the curve because I guessed at where negative 16 was anyway. But you can see our parabola turned upside down. It's really, really, really skinny. Okay. Because we have that horizontal compression of a fourth. Now, your directions in number 3 are really, really important. This polynomial, that's what it is. It's a polynomial. How many x-intercepts does it have? Look at your graph. How many times does it cross the x-axis? None. This doesn't have any x-intercepts. And we've talked about vocabulary, roots, solutions, zeros, the same. And lots of times they are exactly the same as x-intercepts. In this particular problem, they are not the same as x-intercepts. Does this have any roots? Well, that answer is yes. Okay. And we're going to at least start the process of finding those roots. Roots would mean y is 0. So 0 is equal to the opposite of 4x plus 4 quantity squared minus 2. And so we want to solve for x, so we want to get x by itself. Sarah, what would we do first? We would add 2 to both sides. So 2 is the opposite of 4x plus 4 quantity squared. All right, now I still need to get x by itself. Bethany, now what would I do? I divide everything by negative 1. We'll divide everything by negative 1. And we get negative 2 is equal to 4x plus 4 quantity squared. And then here comes the really important part to this problem. All right, now we are still wanting to get x by itself. So somehow I have to undo this squaring. How do you undo squaring something? I do a square root. All right, and if we do it to one side, we're going to have to do it to both sides. So the square root of negative 2 is equal to the square root of 4x plus 4 quantity squared. Okay, now let's pause just a moment, make sure we understand what's going on. So we're taking a square root. A square root means something multiplied by itself. Now the square root of 4 is 2, because 2 times 2 is 4. The square root of 100 is 10, because 10 times 10 is 100. What do you multiply by itself and get negative 2? I wish I could take a picture of Alex's face. It was perfect. We multiply by it together and get a negative. A positive and negative, but that's not the same thing, is it? A square root means the same thing multiplied together. I mean, there's no number on this little number line right here. I don't care what you choose. 1, 2, decimal 18795, negative 3. None of those, if I multiply them together, will I get a negative? This doesn't have any real roots. Now, I want you to take and I want you to underline that word real. Right now, that may not make a huge amount of sense. Why didn't you just say it doesn't have any roots? Now, you actually know the answer to why I didn't say it doesn't have any roots. And you know that answer, even if you don't recognize it yet, because we're going to take this little problem and we're going to take it out of vertex form. We're going to expand it. That doesn't have anything to do with finding our roots. In fact, it would make the roots impossible that right now for you to start to find unless you went back to vertex form. So we're going to multiply this by itself. 4x plus 4 times 4x plus 4. And then we'll subtract 2. So we're going to put this in standard form because I want you to recognize something about this problem. So y is negative 1 times. All right, 4x times 4x gives us what? 16x squared. All right. Now we've got 4x times 4, which is going to give us 16x. 4 times 4x, which is going to give us another 16x. We got all kinds of 16s in this problem. 4 times 4 is going to give us 16. And then we got minus 2. So y is equal to the opposite of 16x squared plus 32x plus 16. And then minus 2. Yes, sir? Yes, but pause just a minute. You're right. I know it doesn't have any real roots because it didn't cross the x-axis. Because the x-axis is real numbers. But I want to illustrate why we underlined the word real. Okay, so y is negative 16x squared minus 32x minus 16, and then minus 2. And I really wouldn't have to go any farther to probably illustrate what we have. But since we started putting this in standard form, we'll finish. So our standard form would be y equals negative 16x squared minus 32x minus 18. Now, we've been working now for 5 weeks to deal with expressions like what we end up with here. We call it a polynomial. What is the degree of this polynomial? 2. If the polynomial has a degree of 2, how many roots does it have? 2. This has 2 roots. It's just those roots are not things that will go on a number line. Well, they're not fake, okay? They're roots that are out here. Think of them as being in front of our board, or they could be behind our board, okay? It's 3-dimensional. They're not sitting on that flat number line, right? Do what? Well, they're in front of it or behind it. They could be also a little bit above it. Right now, I don't want you to worry about where those are. We're going to deal with that when we come back from Thanksgiving, okay? We're going to deal with how do I deal with these numbers that don't fit on a number line, okay? They aren't real. Right? Real doesn't mean they don't exist. Right? It just means they don't fit on a number line. Right? Okay. Are there any questions graphing number 3 with our horizontal compression? All right. So I want to give you a few minutes, and I want you to do problem number 4 and also problem number 5. And while you all are working on that, for those that are here, I'm going to bring you up. We're going to look at your quiz on quadratics. So we're going to take and pull out that half. Now, don't let the fractions scare you to think, oh, I can't do this. It's not drastically different. This is f, not y. F of x is equal to, so we're going to factor out a half. And then I have to think multiplication a little bit. Now, the first part is the easiest part for me. A half times x is going to give me 1/2 x. And then I have to stop and think a little bit. A half times what, or a half of what, will give you 3. Well, you take half of and get 3. 6. I have to get that right to be able to describe the transformations. If I don't factor out that half, I'm going to miss at least one of the transformations. So this is horizontal. It's changing x. And remember, if we're changing x, it's always trying to trick us. We're going to do the opposite. This is like dividing by 2. So we're going to multiply by 2, which is going to make everything bigger. That's a horizontal stretch by 2. Then we're going to come left 6, and we're going to finish by coming up 3. Now, it is my opinion that in general, horizontal stretches are a little easier to do than compressions because I'm not going to have to worry about fractions. So we're dealing with y equals x squared. So our vertex, when we stretch 0, nothing happens. We come left 6. 1, 2, 3, 4, 5, 6, and up 3. So there's our vertex at negative 6, 3. And that is an ordered pair, both an x and a y value. That also tells me where the middle of my graph is, my axis of symmetry, and that x is equal to negative 6. And that's the equation of a line. Anywhere on that line, the x's are negative 6. They don't change. But to draw this graph, I need at least 2 other points. So I'm going to use the fact that on y equals x squared, I have the point 1, 1. So that's the point I'm going to work with. And I'm going to start, and I'm going to horizontally stretch that by 2. So whatever x was, I'm going to double it. That would be 2. And then I'm going to come left 6. So left 1, 2, 3, 4, 5, 6, and up. 1, 2, 3 units. And there we are at negative 4, 4. And then since I know where the middle of my graph is, I know that's 1, 2 units away. So I'm going to go 1, 2 units away. And there we are at negative 8, 4. And I'm ready to draw that graph. And I should notice as I draw the graph, this is a wider graph because of that horizontal stretch. And as I draw that graph, I'm ready to answer, what do you notice about the x-intercepts? There aren't any. Now again, does that mean that this equation has no roots? It's a degree 2 polynomial. It's got 2 roots. They just aren't x-intercepts. Right? They aren't x-intercepts. And so then we can list our domain and range. Our domain here is going to be all reals. We could plug in anything we want for x, and we will get a y value. And our range, as we come from bottom to top, right, the first y value we have down here, right, is at 3. And then those y values keep getting bigger and bigger and bigger and bigger. We're going from 3 to infinity. Any questions at all there in number 4? Okay. Number 5. Now, number 5 has 2 parts. We're going to draw the graph, and we're going to find the zeros. This one has zeros you could find, so it gives us a good place to practice that. Again, the first thing I'm going to do before I can list those transformations is I've got to get x all by itself. I got to pull out that 1/3. So 1/3 times x, 1/3 times 6 will give us 2 plus 3. Now, if you said, Mr. Epling, you do that with so much ease. I'm not that good. That's okay. 1/3 times something, I don't care what letter you choose, it's equal to 2. Now, I don't know what that something is. You don't have a plus 3? I have a plus 3. Okay, well, I'll take out my plus 3. So I'm working the same problem you did. And we'll just cover up our plus 3 here. So it's not there. I liked it a whole lot better plus 3. It was much more interesting. That's okay. All right, let's go back where we were. If you didn't know that was 6, how would you solve this for A, whatever this number is? You'd multiply by 3. That's exactly what we did. Okay? So it's no problem. You don't have to do that all in your head. Okay, so one less transformation since you all didn't have a plus 3. Here's our reflection over the x-axis, and I'm going to abbreviate. Remember, we're changing x, so it's going to try to fool us. We're dividing by 3, so the opposite would be to multiply by 3. We got a horizontal stretch by 3. And then we're going to come right 6. And we're going to see how good you are at finding the zeros in just a minute, but we'll try the graph first. By the way, this is the easiest problem I could ever give you to find the zeros. All right, so we got our vertex. We're on the x-axis at 0, 0, so when we reflect over the x-axis, nothing happens. Stretching 0 by 3, nothing happens. So we're going to come right. 1, 2, 3, 4, 5, 6. So there's a vertex at 6, 0, which means our axis of symmetry is going to run right down the middle of this graph, right here at x equals 6. Even if Mr. Eplin can't draw a straight line with this crazy little pencil. Okay. Now, I need some other points on this graph, so I'm going to use parent function y equals x squared. I'm going to use the point 1, 1 again. That is just an easy point to use. If at all possible, that's what I'm going to do. So I'm going to reflect it over the x-axis. That's 1, -1. Now I'm going to take that x value and I'm going to triple it. Horizontal stretch by 3. So 1 times 3 is 3. And then I'm going to go right. 1, 2, 3, 4, 5, 6. And I'm here at 9, -1. That's a pretty wide looking parabola. And then I'm 1, 2, 3 units away from my midline. 1, 2, 3 units over here on the other side. And I'm ready to draw my graph. Definitely can see it being much, much wider. That's that horizontal stretch. And then in like 30 seconds or less, I'm ready to find the zeros. If I know vocabulary, give me a synonym for zeros. Roots, okay. That's a synonym. Can somebody give me another one? There's 2 more. Do what? Not squares. X-intercepts. That's a very important one in this problem. There's one more. What's our last one? Not degrees. Although degree is important for polynomials. You know, you could let him speak for himself. His mouth works. The other one is solutions. Well, you should have. Loud and proud. Trust yourself. Okay. I like x-intercepts. Because I got a graph. Can you tell me what the x-intercept is? Oh, wait, I know the 0. X equals 6. You see why that's the easiest solution problem you could ever have? But I want you to notice something that's a little different here. We've been talking about this new vocabulary word this week, so I'm going to put it down here. We've been talking about this word multiplicity, because this is important. This is a degree 2 polynomial. How many solutions should it have? Well, what does it look like we have? It looks like we have 1. We don't. Well, we sort of do. We've been talking about multiplicity means how many times a factor is repeated. How many times in this problem do you have x minus 6? You have it twice, right? Squared. You actually have x minus 6 times x minus 6. Now, I actually also have a third times a third. Okay. I'm going to write that as a ninth. But I have x minus 6 times x minus 6 twice. So really, if I'm really listing the solutions, I just have 6 twice. It's repeated. It has a multiplicity of 2. That root, that x-intercept, that factor x minus 6 has a multiplicity of 2. Now look, watch. It's so important. There's something very different about this graph. Normally, I got to go back to one that had an x-intercept. When we come out here to the x-intercept, our graph just goes and it passes right on through. It doesn't stop, it just keeps right on moving. But this time, when we got over here to our x-intercept, what did the graph do? It does hit it, but then what did it do? Did it keep going? It didn't, did it? It got to there, let's call it, it's like it bounced, just like a little ball. It hit that x-axis, and it bounced. Well, that's not really something new. You knew that, because you knew what y equals x squared looks like. That also has a root at x equals 0. Technically, it's got x equals 0 twice, x squared. And when that multiplicity was 2, we hit that little point and we just bounced going the other direction. Okay? That's why we've been starting to talk about multiplicity. Any questions there? Problem number 6. I would do this by factoring and x-intercepts. And I would use those x-intercepts then to find the vertex. The vertex is going to have fractions. There's no way around that in this case. 7 should have been the quickest one you had to graph. I'm just going to use transformations. I don't need any x-intercepts. I don't need any y-intercepts. I'm just going to deal with, hey, I've reflected over the x-axis, vertically stretched by 2, move left 4 and down 5. I would have tried factoring, but it doesn't work. I don't have a choice. I've got to complete the square. So I don't have to give you a problem that says directions say complete the square on the following. Give you something like this, and that's your only option. Okay. And then in problem number 9, okay, I actually would have in this case completed the square. It's actually not bad, because when I factor out the -1, okay, it's pretty easy. You might have tried it with factoring as well. Okay. It doesn't work. So you're going to complete the square. Right. So notice there, of your 4 problems I gave you, 2 of them you need to complete the square with. That's why you've had 3 of those at least almost every single time, right, in the last week for homework. Tonight, you got to look at you. Okay? And I have provided you with answers, right, so that you can check as you go. Because for those of you that are here face-to-face, tomorrow, we have our quadratics test. And for those of you that are home, that'll be Monday. Please do not forget, I sent you a reminder yesterday, but several of you have not finished your weekly review in Math Excel. Don't forget to get that done today, okay, because that's due in the morning. All right, guys, have a great, fabulous day. I'll see you tomorrow. I'm looking forward to what a great job you're going to do on this test.